Good morning, dear students. In yesterday class, we discussed about the angular frequency, time period, and the linear frequency of the vibrating particle or the period when the particle executing the periodic motion. Now, we again discuss about some that last class discussion, that is the angular frequency. The angular frequency of a body which is executing the periodic motion, it means which is moving as a periodic motion. Okay. Here, the angular frequency of a body, it is nothing but a product of linear frequency. This linear frequency we have already denoted as the nu. Here, nu is the linear frequency and a factor. One factor is there. That factor is nothing but one for one period. For one period, the angle should be the 2 pi. Or when it is completely, it completes one revolution, that angle is 2 pi. Or it is 360 degree. So that angle considered as a 2 pi here for one revolution. That's why it is nothing but what? The 2 pi. Its product is that angular frequency is equal to the linear frequency and the 2 pi is a factor. Commonly directly it is right here 2 pi nu, where nu is the linear frequency of a particle which is the reciprocal of the time period. Nu is the linear frequency, it is reciprocal of time period. Then you can write here the nu is equal to 1 by t, that will become what? 2 pi divided by t. This is only for one revolution. This is only for what? One revolution. If the particle makes the n number of revolution, it means the n number of revolution for n revolution, this form will be omega is equal to 2 pi, for into 1 is 1 revolution, into n is n revolution, n 2 pi divided by t. This is for n revolution. Okay, its SI unit is there. 2 pi, it is an angle. 2 pi, an angle. And here the theta is nothing but 2 pi. That is an angle. The unit of angle is radian. And here that t is there. T is nothing but what? Time period. It is in the denominator, so that it become what? The per second. The radian per second is the unit of that angular frequency, or also called angular velocity. Now the next part is displacement of the particle, or displacement of the vibrating particle. What is meant by the displacement of the vibrating particle? If the one particle just starts to vibrate, when here the wave or anything, first one I will give you some example for this one. Okay. The displacement of the vibrating particle is nothing but it is a physical quantity which is changing, which change with time. It means already we have one equation for that. That is y is equal to a into sine of omega t, where a is called what? An amplitude. It is a maximum displacement. Okay, it is constant, which is the constant. And here sine is nothing but what? It is the harmonic function. And omega is the angular frequency. If the particle starts to vibrate like this, if the particle starts to move in a periodic motion, it means what? Like this. Like this, the linear frequency is not constant, it is continuously changing, but the angular frequency is always constant. It means what? The linear velocity is nothing but v. V is continuously changing. It is changing, but the angular frequency or angular velocity is always constant here. This is constant. So that here the angular velocity is also what? Constant. The two terms a and omega both are constant. It is a trigonometric function, is always same. Okay. A and omega both are constant. It means that the displacement of a particle is depends on that time. This displacement is depends on this time. Okay. These two are just variable. Variable terms. It means the displacement, it is a physical quantity which is changing with time in a periodic motion. This is called what? The displacement of the particle. Example for this one. First example is here. I'll write here the example for the displacement of the particle in loaded spring. In loaded spring. I'll draw one diagram for this one. A simple. Okay. Here the displacement of the loaded spring is, I'll take here one rigid support. If it is a rigid support, there is one table. It is a frictionless table. I take a frictionless table here, and one spring is connected to that, and one mass is there, whose mass is m. When you apply some force to that particle, it means if you apply some force F, or if you pull that body, if you just pull that body up to the small displacement, when it starts to displace like this up here, when it comes from its initial position to here. Consider, I take here, I'll draw another diagram. This is the mean position. When you apply the force to this particle, it is just displaced like this. It means the spring is just elongated. The body gets a new position here. It's a mean position. Call this is as a mean position. Okay. When it is asked to move, when it is just spring is just elongated, it gets a new position. It means it just displaced from its initial position here to here. It is a displacement of the body. And again, when you remove that force, it means that is returns to its mean position and it gets the same displacement in the other direction. And it means what? The spring is just compressed like this. Compressed, it means the particle at here now. Don't take here. It just compressed means the particle at here, I think. Okay. It is moving from its mean position at here, from here to here. It is just displaced. It is due to the restoring force. Its compressed is due to the restoring force of the spring. It is just due to the applied force when you pull that body. Okay. In both situations, when the spring is compressed, when the spring is elongated, and both situations, the displacement of the body in both direction of its mean position is always same. These two are always equal to each other. It means the x is equal to x. The displacement. If we take here the y is a displacement, x is equal to y. Both are the same displacement. It means what? It is continuously vibrating from here, elongation, compression, elongation, compression, elongation, compression. It is nothing but what? It is nothing but a periodic motion of this body. Okay. Next, it means in a loaded spring, the displacement of the particle is by the deviation of that body. By the deviation vibrating body or vibrating particle. Next thing is the propagation of sound waves. The sound waves are traveling like this. The sound waves are traveling like this. Okay. When those sound waves are traveling, it means what? If the sound is traveling from here to that end of that classroom or my mouth to that door, it is traveling like this. It displaces some distance from its mean position to here. It is displacement of the wave. And the same as compared to the sound waves, it is propagation of sound waves. It is displaced due to the pressure. The sound is traveling from one end to the another end is due to the pressure. Okay. Next is the propagation of, it is due to the pressure. Okay. Next is the propagation of electromagnetic waves. The electromagnetic waves are also traveling from its mean position to the some distance. These are due to the electric field and the magnetic field is there. This is the electric field and the magnetic field. The electromagnetic waves are just displaced from one position to the another position. Okay. These are the examples for the displacement of the wave which is continuously changing with the time. It means it is continuously it means the displacement of the wave is changing with the time is there. Next concept is the phase. What is mean by phase? Phase is nothing but an angle. The angle made by the vibrating particle at any instant of time which express the position and direction of the particle at that instant. I'll explain here. Okay, at that instant with respect to its mean position. This concept, this sentence is very important. Its mean position. We have to refer its mean position. Okay. Here, I'll explain this phase. Now, phase, when the vibrating particle is vibrated from its mean position, this is called the y displacement of the body. This is the negative direction of that. This is called the mean position of the vibrating particle. When along x-axis there is a time taken by the particle, by the vibrating particle here. When it starts to vibrate, okay, when it starts to vibrate like this, this is some angle made by it. This is called here the phase. It's called phase. If the wave is like this, if the wave is like this, again the phase is just changing. If the wave, it means the amplitude of the wave is more. If the amplitude of the wave is here more, the particle is at here, it means what? The angle is changing, the phase is just changing here like this. Its direction is along y-axis, consider as a y-axis or something here. It is displaced always along x-axis as well as along y-axis continuously with time here. Its direction is like this, and if it is moving like this, the particle is at here, at that instant, at that time, the particle displaces this time. At this position, or it is a 6th second of time, the particle gets a new position. Its direction is here like this. Okay. The direction is just changing from with respect to mean position. We have to refer the mean position here. Its direction is like this. At that instant of time, with respect to mean position, its direction is like this. Now the phase is like this. Phase become what? It's just changing. It is completely omega t. The phase is there. That phase take considered as the phi. consider as a phi or something, or phi not something. It is initial phase. Initial phase, it means the time is 0. Always the initial phase is always 0 because time at the mean position is always 0 here. This is a phase here. Phase means it shows the position and direction of the vibrating particle just with respect to mean position. If it is like this, if it is there, the particle is at here, it is theta, the particle at here, it is the direction of that particle, and this is the angle. Angle is always there. Okay, the angle is theta is there. The theta is considered as a phase. Okay, phase. Just it's a form of, it means the phase form. This phase is always denoted in terms of the harmonic function. Those harmonic functions are here. The phase of vibrating particle is nothing but it is an argument. It is an argument of sine and cosine function, or it is represented in terms of sine function and cosine function to represent the generalized equation of motion. It is nothing but a displacement of the body. The generalized equation in previous equation I written this y is equal to a into sine of theta. Theta is an angle here. Actually, the space is denoted as phi, so that here the theta is equal to phi. Okay. In now idagale continuous now phi theta na phi is ಮಾಡಬೇಕು. Okay. Now in this equation y is equals to a into sine of phi. Phi is a phase here. Totally we consider as that phi as a omega t into phi naught. Omega t plus or minus phi naught. Plus or minus phi naught is there. Okay. When this phi naught is nothing but what? It is the initial phase at t is equal to 0. The time is there. It is y is a displacement of current. It is the negative direction. It is the mean position. The wave is traveling from its mean position. From its mean position to complete one revolution. From its mean position means this is one crest and one trough. There it completes one revolution. Here the time t is 0 at here, t is equal to 0 at mean position. It means what? The initial phase is always 0. Okay. Next, here is the time taken. Okay. The angle is the phase is there. Always phase is there. Okay. Here the angle omega t is also 0, or consider the phi is 0 here at mean position. Angle is 0. It is not started now. Not started here. Then when it comes to the maximum position, the amplitude is maximum here. This is called the maximum displacement of the particle. At that situation, what is the angle here? This angle is pi by 2. Pi by 2 is there. So that I will write when those crossing the time axis. Okay. If it is 0, the angle at here it is pi. To complete one revolution, it takes the angle here 2 pi. The time taken by the particle to complete one revolution is nothing but what? The time taken is t. It means the time taken by the particle to complete one revolution is t here. Then again here t. Then after that, when it starts from, it is the wave. It starts the new wave. It means the particle starts to create the new wave here. From here to again it is the crest and trough is there. Again the second wave is completed. From here to here it is t. From t to here it is 2t. From here to here it is 3t. Yes, exactly. Okay. Okay. Then it is t nothing but, and up to for one revolution is totally t is there. For half revolution, that is t by 2. T by 2 is and it is a time taken by the particle to complete the half wavelength. And the wavelength is there from its mean position to complete one revolution. It is considered as a lambda. Lambda is nothing but the wavelength of the body, or wavelength of the vibrating particle. Wavelength. Yesterday, I written one formula for this one. We have to check. We have to take here. The phase, it is nothing but the angle. Yesterday, I written one formula. We have to calculate the phase difference, path difference, as well as the time difference here. The phase difference is there. The phase difference right here, what is that? Delta phi, change in phase, divided by, for one revolution, the total angle is 2 pi. It is divided by pi, 2 pi. And the path difference is there. The path difference is considered as the x. Okay, sorry, it is delta x. Difference is there, na? Delta x divided by what is the distance for one revolution? The distance is nothing but what? Wavelength. Length is the distance here. Okay, lambda, and which is equals to what? The time difference. The time difference, that is delta t. Sorry, it is delta into small t divided by what is the time taken for one revolution? That is t. Just using this one formula, we can calculate the time difference, path difference, and also the phase difference, path difference, and also the time difference here. Okay, just we have to take here the initial phase is 0. The initial phase is 0 because it is initial phase always at t is equal to 0. Here the initial phase is 0 at t is equal to 0 means here the initial phase is always 0. Okay. If the initial phase is 0, then take that y is equal to a into sine of phi. If you take that phi as here, the phi is equal to omega t plus of phi naught. If it makes the certain angle that is omega t at its mean position, the phi is 0, it is nothing but omega t is 0. If the initial phase is 0, okay, initial phase is 0 is nothing but phi is equals to omega. Okay. Next, it is like that, this one. Then this equation y is equal to a into sine of omega t plus or minus phi naught. Plus or minus phi naught. Is always, initial phase is always 0 here. It means the phase of the particle, it is an argument, sine or sine function, which represent the generalized equation of motion. That represent the generalized equation is nothing but displacement of the equation, displacement of the vibrating particle, or the x is a displacement along x-axis and its component. That become what? A is an amplitude is constant cos of omega t plus or minus of phi naught. When phi naught is the initial phase at time t is equal to 0. Okay? Yes. So what is the angle of this phase? It is the unit of phase. Unit of phase. Phase is nothing but what? It is an angle. Phase is nothing but an angle. That angle is, the unit of angle is nothing but what? It is a radian. A radian is unit of phase. Okay? Yes. Now the initial phase is there. Okay, it is completed. When this becomes 0 at, I'll remove this one. The last thing is here, very small part is there. The last thing is at t is equal to 0. At t is equal to 0, this omega t is equal to what? 0. Okay. At t is equal to 0, omega t is equal to what happened? It is also 0. If it is 0, then what about the phase? That phase is pi is equal to omega t plus or minus of phi naught is there. If it is 0, then what happened? It is always phi naught. It is 0 now. Okay. Phi is equal to phi naught is there. Okay. This is considered as an initial phase. This is considered as what? The initial phase. Okay. Then in next class we will discuss about the phase difference if the two vibrating particles, if the two particles are vibrating in same phase or opposite phase. Okay. Same phase means always same phase means what? If it is positive direction, same phase. If those two particles are moving in negative direction, same phase. When those are moving in opposite direction means what? One is moving in the positive direction, one is moving in the negative direction. Opposite direction. Okay. These two are the same phase and the opposite phase. We'll discuss in next class. Okay. Thank you.